Right now, you're spinning at over 1,000 miles per hour. You can't feel it, but it's happening. And that's not even the crazy part. You're simultaneously whirling through space at speeds that make bullets look frozen. But here's what will really mess with your head. Scientists have never found a single object in the universe that isn't rotating. Not one. Ever. From the electrons in your coffee to supermassive black holes, from invisible dark matter halos to the entire cosmic web, everything spins. And this isn't cosmic coincidence. There's a profound reason why the universe literally cannot stand still, why stillness itself is forbidden by the laws of physics. If you're fascinated by these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. Now let's begin. Look at your hand. Right now, the electrons in every atom of your body are zipping around their nuclei at speeds approaching 2 million meters per second. The Earth beneath your feet is rotating at about 1,600 kilometers per hour at the equator. Our planet is simultaneously orbiting the Sun at 30 kilometers per second. Our entire solar system is wheeling around the Milky Way's center at 220 kilometers per second. And our galaxy itself is moving through space at 600 kilometers per second towards something called the Great Attractor. You're not just sitting still, you're on the wildest ride in the universe and you don't even feel it. This universal spinning isn't random chaos. It emerges from fundamental laws of physics that have been operating since the first moments after the Big Bang, 13.8 billion years ago. The story of why everything spins is really the story of the universe itself, a tale of gravity, angular momentum, and the beautiful mathematics that govern reality. Let's start with something called angular momentum, because without understanding this concept, nothing else will make sense. Imagine you're sitting on a spinning office chair with your arms spread wide. When you pull your arms close to your body, you spin faster. This isn't magic, it's conservation of angular momentum, one of the most fundamental principles in physics. Angular momentum depends on three things: how much mass you have, how fast you're rotating, and how that mass is distributed. When you pull your arms in, you're not changing your mass or your angular momentum, but you're changing how your mass is distributed, which forces your rotation speed to increase. This same principle explains why figure skaters spin faster when they pull their arms in, why pizza dough flattens when tossed and spun, and, here's where it gets cosmic, why stars, planets, and galaxies spin the way they do. The universe doesn't have a choice about this. Angular momentum must be conserved. It's as fundamental as the conservation of energy. But where did all this angular momentum come from in the first place? To answer that, we need to go back to the beginning, not just the beginning of our solar system, but the beginning of everything. In the first fraction of a second after the Big Bang, the universe was an incredibly hot, dense soup of fundamental particles. Tiny quantum fluctuations, random variations in density and motion that occur at the smallest scales, meant that particles weren't perfectly evenly distributed. Some regions were slightly denser, others slightly less dense. Some particles moved slightly this way, others slightly that way. These minuscule variations might seem insignificant, but they were the seeds of everything we see today. As the universe expanded and cooled, gravity began to amplify these tiny differences. Denser regions attracted more matter, becoming even denser. And here's the crucial part. Whenever particles or clouds of gas fall toward each other under gravity's pull, they almost never fall in perfectly straight lines. Even the tiniest sideways motion, what physicists call transverse velocity, gets amplified as matter collapses. Think about draining water from a bathtub. The water never goes straight down the drain. It forms a vortex, a whirlpool, because even the slightest rotation gets concentrated and accelerated as the water converges toward the drain. The same thing happens on cosmic scales, except instead of water and drains, we're talking about gas clouds and gravity. The European Space Agency's Planck satellite has mapped these primordial fluctuations in extraordinary detail. By studying the cosmic microwave background, the afterglow of the Big Bang, scientists can see the tiny temperature variations that represent the density fluctuations from when the universe was only 380,000 years old. These fluctuations, typically just 1 part in 100,000, were enough to set everything in motion. Every spinning galaxy we see today can trace its rotation back to these ancient quantum fluctuations. Now let's zoom forward to about 4.6 billion years ago, to a massive cloud of gas and dust called the Solar Nebula, the birthplace of our solar system. This cloud, probably about 2 light-years across, was already rotating slowly, carrying angular momentum inherited from the galaxy's overall rotation and from turbulent motions within the interstellar medium. The cloud might have been spinning lazily, taking millions of years to complete one rotation, but it was spinning nonetheless. Then something happened. Perhaps a nearby supernova explosion sent shockwaves through the cloud, or maybe it simply reached a critical density. The cloud began to collapse under its own gravity. And this is where conservation of angular momentum becomes spectacular. As that enormous cloud contracted, it had to spin faster, just like our figure skater pulling in their arms. A cloud 2 light-years across collapsing to the size of our solar system, about 100 astronomical units, would increase its rotation speed by a factor of thousands. But the cloud couldn't just collapse into a spinning ball. The rotation created what physicists call centrifugal force, really just the tendency of spinning objects to fly outward. In the direction of spin, this outward force balanced gravity, preventing collapse. But perpendicular to the spin axis, there was no such resistance. The cloud flattened into a disk like pizza dough spun by a master chef. This is why our solar system is flat, why Saturn's rings are flat, why spiral galaxies are flat. It's geometry imposed by physics. The Atacama Large Millimeter Array in Chile has captured stunning images of these protoplanetary disks forming around young stars throughout our galaxy. We can literally see other solar systems being born, watching the same process that created our home playing out across the cosmos. In the Orion Nebula alone, we've observed hundreds of these spinning disks, each one a potential solar system in the making. At the center of our collapsing cloud, material accumulated into what would become the Sun. As more and more gas fell inward, our proto-sun spun faster and faster. Today, our Sun completes one rotation in about 25 days at its equator. Though interestingly, because the Sun isn't solid, different latitudes rotate at different speeds, a phenomenon called differential rotation that also occurs on gas giant planets like Jupiter. The remaining material in the disk began to clump together through a process called accretion. Tiny dust grains stuck together through electrostatic forces. These grew into pebbles, then boulders, then planetesimals, bodies kilometers across. At each stage, when 2 objects collided and stuck together, their individual rotations combined. If they were spinning in the same direction, the resulting objects spun faster. If they were spinning in opposite directions, they might cancel out some rotation. But statistically, because everything was orbiting the Sun in the same direction, most collisions added to the overall spin. The planets formed from countless such collisions, each one adding or subtracting angular momentum. This is why Venus spins backward, what astronomers call retrograde rotation. At some point in its history, Venus likely suffered a massive collision that reversed its spin. In fact, Venus rotates so slowly that a day on Venus, one complete rotation, takes longer than a year on Venus, one complete orbit around the Sun. It's the cosmic equivalent of getting hit so hard you spin backward in slow motion. Uranus has an even stranger story. This ice giant is tilted at 98 degrees, essentially rolling on its side as it orbits the Sun. Computer simulations suggest Uranus was struck by an Earth-sized object early in its history, knocking it completely sideways. The Spitzer Space Telescope and ground-based observations have helped us understand these ancient collisions by studying the current composition and structure of these planets. But not everything in our solar system spins the same way. While most moons orbit in the same direction their planets rotate, what we call prograde motion, some moons rebel. Neptune's largest moon, Triton, orbits backward. This retrograde orbit tells us Triton wasn't born around Neptune, but was captured from the Kuiper Belt, probably a dwarf planet that ventured too close and got caught by Neptune's gravity. Triton's backward orbit is slowly decaying, and in about 3.6 billion years, it will either crash into Neptune or be torn apart into a spectacular ring system. The dance of celestial bodies gets even more intricate when we consider binary systems, two objects orbiting around their common center of mass. About half of all stars in our galaxy exist in binary or multiple star systems, and these cosmic partnerships create some of the most extreme spinning objects in the universe. When two stars orbit each other closely, they can exchange material, spinning each other up to incredible speeds. The LIGO and Virgo gravitational wave detectors have detected dozens of binary black hole mergers, where two black holes spiral toward each other, spinning faster and faster until they collide in a cataclysmic event that literally ripples the fabric of spacetime. Speaking of extreme cosmic phenomena, if you're fascinated by the unusual and extraordinary in our universe, check out my video called "What is the Rarest Object in the Universe?", where we explore cosmic oddities that shouldn't exist but do. The link is in the description and pinned on the comments. Now back to our spinning cosmos. Jupiter's Great Red Spot showcases another aspect of rotation, vortices within rotating systems. This storm, larger than Earth and raging for at least 350 years, is essentially a giant hurricane maintained by Jupiter's rapid rotation. Jupiter completes a rotation in just under 10 hours despite being 11 times wider than Earth. This incredible spin rate creates powerful jet streams and enables storms that would be impossible on slower rotating worlds. The Juno spacecraft, currently orbiting Jupiter, has revealed that these storms extend deep into the planet's interior, with routes reaching down 3,000 kilometers. But Jupiter's moons tell an even more fascinating story about rotation. Io, Europa, Ganymede, and Callisto, the four largest moons discovered by Galileo in 1610, are all tidally locked to Jupiter. This means they rotate exactly once per orbit, always showing the same face to their parent planet. It's not coincidence, it's physics. Tidal forces from Jupiter's immense gravity gradually synchronize their rotation with their orbital period over millions of years. Our own moon is tidally locked to Earth for the same reason. The moon's gravity creates tides in Earth's oceans, but Earth's gravity also creates tides in the moon's solid rock. These rock tides act like brakes, gradually slowing the moon's rotation until one face permanently faces Earth. This is why we only see one side of the moon, the near side, while the far side remained hidden from human eyes until the Soviet Luna 3 probe photographed it in 1959. This tidal locking isn't instantaneous, it's a gradual process that takes millions of years. And it works both ways. The moon is actually slowing Earth's rotation too. 400 million years ago, an Earth day was only 22 hours long. The moon is steadily retreating from Earth at about 3.8 centimeters per year, roughly the speed your fingernails grow. And as it moves away, it takes some of Earth's rotational energy with it. Eventually, billions of years from now, Earth and the moon will be mutually tidally locked, with the same sides always facing each other, like two dancers frozen in an eternal embrace. The Kepler Space Telescope and its successor, TESS, the Transiting Exoplanet Survey satellite, have discovered thousands of exoplanets, many of which are likely tidally locked to their stars. These worlds, particularly those orbiting red dwarf stars, might have one side in permanent daylight and another in eternal darkness. The Terminator line, the boundary between day and night, might be the only habitable region on such planets, creating ribbon worlds where life, if it exists, would be confined to a narrow twilight zone. Now let's venture beyond planets to see rotation on truly cosmic scales. Galaxies are perhaps the most majestic examples of cosmic rotation. Our Milky Way, a barred spiral galaxy containing hundreds of billions of stars, completes one rotation every 225 million years, what astronomers call a galactic year. The last time our solar system was in this position in the galaxy, dinosaurs were just beginning to emerge on Earth. But here's where dark matter enters our story, adding a profound mystery to galactic rotation. In the 1970s, astronomer Vera Rubin made observations that shattered our understanding of galaxies. She studied how fast stars orbit around galactic centers and discovered something impossible. Stars at the edges of galaxies were moving just as fast as those near the center. This violated everything we knew about gravity and rotation. According to Newton's laws and Kepler's orbital mechanics, objects farther from a gravitational center should move more slowly. Mercury orbits the Sun much faster than Neptune. Satellites close to Earth orbit faster than those farther away. But in galaxies, this rule seemed broken. Stars at the edge should be flying off into intergalactic space given their speeds, yet galaxies remain stable for billions of years. Rubin's solution was radical. Galaxies must contain far more mass than we can see. This invisible mass, dark matter, forms enormous halos around galaxies, providing the extra gravity needed to hold those speeding outer stars in place. Today, we believe dark matter makes up about 85% of all matter in the universe. We can't see it, we can't touch it, but we can observe its gravitational effects on galactic rotation. The way galaxies spin is our strongest evidence that most of the universe is made of something completely unknown to science. The European Space Agency's Gaia spacecraft is currently mapping the positions and velocities of over 1 billion stars in our galaxy with unprecedented precision. This data is revealing the complex patterns of rotation within the Milky Way, including density waves that create our galaxy's spiral arms and stellar streams, remnants of smaller galaxies torn apart by our galaxy's rotation and gravity. Some galaxies spin in truly bizarre ways. The Hubble Space Telescope has observed galaxies that rotate backward relative to their neighbors, galaxies with counter-rotating cores where the center spins opposite to the outer regions, and even galaxies that appear to have stopped rotating altogether, so-called pressure-supported elliptical galaxies where random stellar motions dominate over organized rotation. At even larger scales, galaxy clusters, collections of hundreds or thousands of galaxies bound by gravity, show complex rotational patterns. While the cluster as a whole might not rotate like a rigid body, individual galaxies orbit around the cluster's center of mass, creating a cosmic dance spanning millions of light-years. The Coma cluster, about 300 million light-years away, contains over 1,000 galaxies all swooping around their common center, taking billions of years to complete single orbits. But perhaps the most extreme example of cosmic rotation comes from neutron stars, the collapsed cores of massive stars that have exploded as supernovae. When a star many times more massive than our Sun exhausts its nuclear fuel, it collapses catastrophically. The outer layers explode outward in a supernova, but the core collapses inward, crushing matter to unimaginable densities. A neutron star packs more mass than our Sun, into a sphere just 20 kilometers across. A teaspoon of neutron star material would weigh about 5 billion tons on Earth. Remember conservation of angular momentum? When that massive stellar core collapses from hundreds of thousands of kilometers across to just 20 kilometers, its rotation rate increases dramatically. The fastest spinning neutron star we've discovered, PSRJ 1748-2446, rotates 716 times per second. Let that sink in. This city-sized object, weighing more than our Sun, spins 716 times every second. Its surface moves at about 1/4 the speed of light. At its equator, the centrifugal force is so strong it nearly tears the star apart. These rapidly spinning neutron stars, called pulsars when their radiation beams sweep past Earth like cosmic lighthouses, are the most precise clocks in the universe. The Fermi Gamma-Ray Space Telescope has detected over 200 of these gamma-ray pulsars, helping us understand how these extreme objects convert rotational energy into radiation. Some pulsars are so regular that they rival atomic clocks in precision, losing less than 1 second over millions of years. The fastest spinning pulsar was discovered by the Green Bank Telescope in West Virginia, and follow-up observations by the Chandra X-ray Observatory revealed it's in a binary system with a companion star. The pulsar is actually consuming its companion, using the infalling material to spin even faster, a process astronomers call recycling that can resurrect old, slow pulsars into millisecond pulsars spinning hundreds of times per second. Black holes represent the ultimate extreme of cosmic rotation. When massive stars collapse or when matter falls into a black hole, angular momentum must still be conserved. The result is a spinning black hole described by something called the Kerr metric in Einstein's general relativity. These rotating black holes, called Kerr black holes, drag space-time around with them in a phenomenon called frame dragging or the lens-thirring effect. Near a rotating black hole, space itself is twisted into a whirlpool. Nothing can remain stationary near a spinning black hole. Everything must rotate in the same direction as the black hole, carried along by the twisted fabric of space-time itself. This region, called the ergosphere, is where the impossible becomes possible. Theoretically, you could extract energy from a rotating black hole by dropping matter into the ergosphere and having it escape with more energy than it entered with, a process called the Penrose process, proposed by physicist Roger Penrose in 1969. The Event Horizon Telescope collaboration, which produced the first image of a black hole in 2019, showed us the supermassive black hole at the center of galaxy M87. This monster, weighing 6.5 billion times our Sun's mass, is spinning at nearly 90% of the maximum speed allowed by Einstein's relativity. The glowing ring we see in that historic image is actually lopsided because of the black hole's rotation. One side appears brighter because material rotating toward us gets boosted by relativistic effects. In 2022, the same collaboration revealed the first image of Sagittarius A star, the supermassive black hole at our galaxy's center. This black hole, 4 million times our Sun's mass, spins much more slowly, completing one rotation in about 11 minutes. Even at this leisurely pace, it warps space-time so severely that stable orbits close to the black hole can only exist if they align with its rotation. Objects trying to orbit backward would be flung away or dragged into alignment. The spin of black holes affects entire galaxies. Active galactic nuclei, galaxies with feeding supermassive black holes at their centers, launch jets of material at nearly light speed. These jets, which can extend for millions of light years, are powered by the black hole's rotation. Magnetic field lines threading through the ergosphere get twisted into cosmic springs, accelerating particles to tremendous energies. The Very Large Array Radio Telescope and the Chandra X-ray Observatory have mapped these jets in stunning detail, showing how a spinning black hole, no bigger than our solar system, can influence regions larger than entire galaxy clusters. But rotation isn't just a large-scale phenomenon. It exists at the quantum level too, in ways that challenge our everyday understanding of spinning. Electrons, protons, and neutrons have a property called spin, but it's not really spinning in the classical sense. An electron's quantum spin is an intrinsic form of angular momentum that can only point up or down relative to any axis you choose to measure. It's quantized. It can't be just any value, only specific discrete amounts. This quantum spin is responsible for magnetism. When electrons in iron atoms align their spins, their tiny magnetic fields add up to create a macroscopic magnet. The Earth's magnetic field, which protects us from solar wind and cosmic rays, ultimately arises from the quantum spins of electrons in molten iron churning in our planet's outer core. The Swarm satellite mission is currently mapping Earth's magnetic field in unprecedented detail, showing how it changes and even reverses over geological time. Quantum spin also explains why matter is stable. The Pauli exclusion principle states that no two electrons can occupy the same quantum state. They can't have identical positions, energies, and spins. This prevents all electrons in an atom from collapsing into the lowest energy level. Without quantum spin, atoms couldn't exist as we know them, chemistry would be impossible, and the universe would be a very different place. The Large Hadron Collider at CERN uses the spin properties of particles to probe the fundamental nature of reality. When protons collide at nearly light speed, the spin states of the resulting particles tell physicists about the forces and interactions at play. The discovery of the Higgs boson in 2012 was confirmed partly through analyzing the spin properties of particles produced in countless collisions. Now here's something that will blow your mind. The entire universe might be rotating. This sounds impossible. Rotating relative to what? But some cosmologists have seriously investigated this possibility. If the universe has even the tiniest overall rotation, it would show up as subtle patterns in the cosmic microwave background radiation. The Planck satellite looked for these patterns and found nothing. If the universe is rotating, it's doing so incredibly slowly, less than once over its entire 13.8 billion-year history. But individual regions of the universe do show interesting rotational patterns. In 2020, researchers analyzing data from the Sloan Digital Sky Survey discovered that galaxies tend to rotate in certain directions depending on their location in the cosmic web, the largest structure in the universe. It's as if different regions of the universe have preferred spin directions, possibly inherited from turbulence in the early universe or from the gravitational influence of massive cosmic structures. The cosmic web itself, vast filaments of dark matter and galaxies stretching across billions of light-years, shows signs of rotation. Simulations run on supercomputers like the Summit system at Oak Ridge National Laboratory suggest these filaments spin slowly, taking billions of years to complete one rotation. If confirmed by observations, this would be the largest rotating structures ever discovered, making galaxies look tiny by comparison. Even empty space might rotate, at least in theory. Solutions to Einstein's field equations, like the Gödel metric, discovered by mathematician Kurt Gödel in 1949, describe universes where spacetime itself rotates. In such a universe, closed time-like curves could exist, paths through spacetime that loop back to their starting point in both space and time. You could, theoretically, travel into your own past. Fortunately, or unfortunately, depending on your perspective, we don't live in such a universe. Let's bring this back to Earth for a moment. Our planet's rotation affects everything about our daily lives, often in ways we don't realize. The Coriolis effect caused by Earth's rotation deflects moving objects to the right in the northern hemisphere and to the left in the southern hemisphere. This shapes weather patterns, ocean currents, and even the direction hurricanes spin. Without Earth's rotation, we'd have no trade winds, no Gulf Stream, no jet streams. Weather patterns would be completely different, likely featuring permanent convection cells with hot air rising at the equator and cold air sinking at the poles. Earth's rotation also creates our magnetic field through a process called the geodynamo. Liquid iron in the outer core, driven by convection and twisted by rotation, generates electric currents that produce our protective magnetic shield. Mars, which rotates at nearly the same rate as Earth but lacks a liquid outer core, has almost no magnetic field. As a result, solar wind has stripped away most of Mars's atmosphere over billions of years. The MAVEN spacecraft orbiting Mars has measured this atmospheric loss in real time, showing us what might have happened to Earth without our spinning, molten core. The length of Earth's rotation, our day, affects all life on our planet. Circadian rhythms, the biological clocks that regulate sleep, hormone production, and countless other processes, evolved to match Earth's 24-hour rotation. Experiments on the International Space Station, where astronauts experience 16 sunrises and sunsets per day, show how disrupted light-dark cycles affect human health, causing sleep problems, decreased cognitive performance, and increased health risks. Plants also respond to Earth's rotation. Through a process called heliotropism, sunflowers and many other plants track the sun across the sky during the day, then reset overnight to face east again. This daily dance, synchronized with Earth's spin, maximizes photosynthesis. Even trees show the effects of rotation. Growth rings are often denser on one side due to prevailing winds shaped by the Coriolis effect. Ocean tides, while primarily caused by the Moon's gravity, are profoundly influenced by Earth's rotation. The rotating Earth carries continents and ocean basins through tidal bulges, creating the complex patterns of high and low tides we observe. Tidal friction, the drag of tidal bulges against the rotating Earth, is gradually slowing our planet's spin and pushing the Moon away. Fossil corals from 400 million years ago show growth patterns indicating Earth then had 400 days per year, each lasting about 22 hours. Even technology must account for rotation. GPS satellites must correct for Earth's rotation to provide accurate positioning. Their clocks must also account for relativistic effects, time dilation from their orbital velocity, and gravitational time dilation from being farther from Earth's center. Without these corrections, GPS would accumulate errors of about 10 kilometers per day. The Laser Interferometer, Gravitational Wave Observatory or LIGO, which detects ripples in spacetime from colliding black holes and neutron stars, must account for Earth's rotation in its calculations. The detectors are so sensitive they can measure distortions smaller than 1,000th the width of a proton. Earth's rotation creates a constant background signal that must be filtered out to detect genuine gravitational waves from cosmic events. Looking deeper into space, we find that rotation plays a crucial role in star formation. The Orion Nebula, visible to the naked eye as the middle star in Orion's sword, is a stellar nursery where we can watch stars being born. The Hubble Space Telescope has revealed over 150 protoplanetary disks in this region alone, each one a solar system in formation. These disks, called proplyds, show us that rotation is essential to starbirth. Without rotation, collapsing gas clouds would simply fall straight into the forming star. But angular momentum forces the material into a disk, allowing planets to form from the leftover material. The ALMA telescope in Chile has captured breathtaking images of these forming systems, showing gaps in the disks where planets are clearing their orbits. we're literally watching the same process that created Earth 4.6 billion years ago. In the young star HL Tauri, just 1 million years old, ALMA revealed multiple rings and gaps in its protoplanetary disk, suggesting planets are already forming. This star system is giving us a time machine view of our own solar system's birth. Rotation even determines what kinds of stars can form. The initial rotation rate of a collapsing gas cloud affects whether it forms a single star, a binary system, or a multiple star system. Too much rotation and the cloud fragments into multiple stars. Too little and you get a single, slowly rotating star. Computer simulations run on supercomputers like Japan's Fugaku show that most star-forming regions produce multiple stars because turbulence in molecular clouds creates numerous rotating eddies that collapse independently. The death of stars is equally influenced by rotation. When massive stars explode as supernovae, their rotation affects how the explosion proceeds. Rapidly rotating stars can produce some of the most energetic events in the universe, long-duration gamma-ray bursts. These jets of radiation powered by the collapsing star's rotation can be detected from billions of light-years away. The Swift and Fermi space telescopes detect about 1 gamma-ray burst per day, each one marking the death of a massive, rapidly rotating star in a distant galaxy. Core collapse supernovae themselves are asymmetric because of rotation. The rotating core doesn't collapse uniformly, it pancakes perpendicular to the spin axis. This asymmetry can actually help drive the explosion, converting rotational energy into explosive power. The supernova 1987A, the nearest observed supernova in modern times, showed clear signs of asymmetric explosion with material ejected preferentially along the rotation axis. Rotation creates some of the most beautiful structures in space. Planetary nebulae, the glowing shells of gas expelled by dying sun-like stars, often show stunning bipolar shapes sculpted by rotation. The Cat's Eye Nebula, the Butterfly Nebula, and the Hourglass Nebula all showcase how rotation and magnetic fields shape stellar death into cosmic art. The shells of gas are channeled along the star's rotation axis, creating intricate patterns that the Hubble Space Telescope has captured in magnificent detail. Binary star systems, where two stars orbit each other, create even more complex rotational dynamics. In close binary systems, stars can transfer material between each other, creating accretion disks that spiral onto the receiving star. This process powers some of the brightest objects in the universe. Cataclysmic variables, binary systems where a white dwarf steals material from a companion star, can brighten by factors of thousands when accumulated material undergoes thermonuclear explosion on the white dwarf's surface. X-ray binaries, where a neutron star or black hole pulls material from a companion star, are among the brightest X-ray sources in the sky. The infalling material forms an accretion disk that heats up to millions of degrees through friction, emitting X-rays detectable by telescopes like NASA's NuSTAR and ESA's XMM Newton. The rotation of these disks creates quasi-periodic oscillations, regular flickering in brightness that tells us about the extreme physics near compact objects. In some binary systems, both stars are compact objects, 2 white dwarfs, 2 neutron stars, or even 2 black holes. These systems slowly spiral together as they emit gravitational waves, ripples in spacetime predicted by Einstein. The orbital decay of binary pulsars provided the first indirect evidence for gravitational waves, earning the 1993 Nobel Prize in Physics. Now LIGO and Virgo directly detect these waves, having observed over 90 binary mergers since 2015. The most spectacular mergers involve neutron stars. When 2 neutron stars collide, they create a kilonova, an explosion that forges heavy elements like gold, platinum, and uranium. The merger GW170817, detected in 2017, was observed by telescopes across the electromagnetic spectrum. This single event produced about 10 Earth masses of gold and confirmed that many of Earth's heavy elements came from neutron-star collisions. The gold in your jewelry was literally forged in the collision of two city-sized objects spinning hundreds of times per second. Rotation affects how galaxies evolve and interact. When galaxies collide, a process that takes hundreds of millions of years, their individual rotations determine the outcome. If they're rotating in the same direction, they might merge smoothly. If rotating oppositely, the collision is more violent, triggering massive bursts of star formation. The antennae galaxies, two spirals in the process of merging, show how rotation shapes galactic collisions into spectacular cosmic sculptures. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4.5 billion years, these two rotating spirals will begin their cosmic dance. Simulations show they'll pass through each other multiple times before eventually merging into a single, elliptical galaxy. Despite containing over 1 trillion stars combined, virtually no stars will actually collide. Space is just that empty. But the galaxy's rotations will be completely disrupted, transforming two elegant spirals into one football-shaped elliptical. The Gaia Space Telescope has revealed that our galaxy's rotation is more complex than we thought. The Milky Way's disk is warped like a vinyl record left in the sun, and this warp precesses, rotates around the galaxy. Stars at different heights above and below the galactic plane orbit at slightly different rates, creating a wave pattern that ripples through the galaxy. We've also discovered that the Milky Way's rotation speed has been affected by close encounters with smaller galaxies, including one that grazed us about 600 million years ago. Dark energy, the mysterious force accelerating the universe's expansion, might affect cosmic rotation in ways we don't yet understand. Some theories suggest dark energy could cause rotating objects to spin down over cosmic time, though this effect would be incredibly tiny. Other theories propose that dark energy itself might have a rotational component, though current observations show no evidence for this. The strangest rotation in the universe might be that of strange stars, hypothetical objects made of strange quark matter. If they exist, these objects could rotate even faster than neutron stars because they're held together by the strong nuclear force rather than gravity. Theoretical models suggest strange stars could rotate over 3,000 times per second without flying apart. Some astronomers think certain unusual pulsars might actually be strange stars, though this remains highly controversial. Primordial black holes, if they exist, would carry information about rotation in the very early universe. These hypothetical black holes, formed in the first second after the Big Bang, would have preserved the angular momentum of the tiny regions that collapsed to form them. Detecting primordial black holes would give us a window into the universe's rotation state when it was less than a second old. Even more exotic are cosmic strings, hypothetical, one-dimensional defects in spacetime that might have formed during phase transitions in the early universe. If cosmic strings exist and rotate, they could create closed time-like curves, allowing time travel into the past. Rotating cosmic strings could also gravitationally lens distant galaxies in distinctive patterns. Though we haven't found any cosmic strings yet, telescopes continue to search for their signatures. The rotation of the universe ties into deep questions about the nature of time and causality. In general relativity, rotation and time are intimately connected. The Lenz-Thirring effect around rotating masses doesn't just drag space, it drags time. Clocks at different positions around a rotating black hole tick at different rates, not just because of gravitational time dilation, but because of the rotation itself. At the quantum scale, rotation reveals the bizarre nature of reality itself. Particles have intrinsic angular momentum, spin, but this spin doesn't correspond to actual rotation in space. An electron's spin is always the same magnitude, whether you measure it as up or down along any axis. Even stranger, electrons are point particles with no size, yet they somehow possess angular momentum. It's as if the universe has rotation built into its fundamental structure, existing even where there's nothing to actually rotate. This quantum spin leads to one of nature's most profound symmetries. The spin statistics theorem, proven by Wolfgang Pauli in 1940, shows that particles with integer spin, bosons, can pile up in the same quantum state, while particles with half-integer spin, fermions, cannot. This seemingly abstract mathematical rule explains why matter has structure. Electrons, being fermions, must occupy different energy levels in atoms, creating the shell structure that gives rise to chemistry. Photons, being bosons, can all occupy the same state, making lasers possible. The connection between spin and statistics has cosmic consequences. In the early universe, when temperatures exceeded trillions of degrees, the behavior of particles was dominated by their quantum statistics. The ratio of matter to antimatter, the formation of the first atomic nuclei, even the seeds of cosmic structure, all were influenced by whether particles were fermions or bosons, spinners or non-spinners in the quantum sense. Superfluidity and superconductivity, states of matter with zero viscosity and zero electrical resistance, arise from quantum rotation. In superfluid helium, atoms form a quantum condensate that can flow without friction. Vortices in superfluids are quantized. They can only rotate at specific speeds determined by Planck's constant. Scientists have created superfluids in laboratory conditions that model neutron star interiors, where superfluid vortices might trigger pulsar glitches, sudden speed-ups in neutron star rotation. The European Space Agency's LISA mission, planned for launch in the 2030s, will detect gravitational waves from rotating binary systems across the universe. Unlike LIGO, which detects high-frequency waves from stellar mass objects, LISA will observe low-frequency waves from supermassive black hole binaries. These monsters, millions to billions of times our Sun's mass, spiral together over millions of years, their rotation encoding information about galaxy formation and the growth of structure in the universe. Speaking of supermassive black holes, recent observations have revealed that many rotate at nearly the maximum rate allowed by physics. The black hole in galaxy NGC 1365 spins at 99.9% of the theoretical maximum. At this speed, the event horizon itself is dragged around at nearly light speed. Space and time become so twisted that closed time-like curves almost form. Push just a bit harder, and causality itself would break down. The spin of supermassive black holes affects entire galaxies through a process called AGN feedback. When black holes feed on surrounding material, their rotation powers jets that heat and expel gas from the galaxy, shutting down star formation. This feedback loop regulates galaxy growth. Without it, galaxies would be much more massive than we observe. The balance between black hole rotation, jet power, and galaxy evolution is one of the key relationships governing cosmic structure. In 2021, the Event Horizon Telescope collaboration detected magnetic fields around the M87 black hole, revealing how rotation organizes these fields into helical patterns that launch jets across millions of light-years. These magnetic fields, anchored in the spinning spacetime itself, act like cosmic particle accelerators, producing some of the highest energy particles in the universe. Closer to home, we're discovering that asteroids and comets have complex rotational states that tell stories of their histories. The asteroid Bennu, visited by NASA's OSIRIS-REx mission, spins faster over time due to the Yorp effect. Sunlight heating one side more than the other creates a tiny torque. Bennu is spinning so fast that rocks are flying off its surface, and it might eventually spin itself apart. The sample returned from Bennu in 2023 contains material from the solar system's birth, preserved by the asteroid's gentle rotation for billions of years. Comet 67P Churyumov-Gerasimenko, explored by ESA's Rosetta mission, showed us how rotation shapes small bodies. This rubber duck-shaped comet rotates once every 12 hours, and its spin axis has shifted due to outgassing. Jets of vapor from sublimating ice act like tiny rockets, gradually changing the comet's rotation. Rosetta observed landslides and structural changes caused by rotational stresses, showing that even small bodies are dynamically evolving due to their spin. The dwarf planet Haumea, discovered in 2004, is one of the strangest rotators in our solar system. Shaped like an elongated egg, it spins once every 4 hours, so fast that it's stretched into an ellipsoid twice as long as it is wide. Haumea even has rings discovered in 2017 when it passed in front of a distant star. This rapid rotation probably resulted from a massive collision that also created Haumea's 2 small moons. Saturn's moon. Hyperion tumbles chaotically, its rotation unpredictable beyond a few weeks. This chaotic rotation results from its irregular shape and gravitational interactions with Saturn and Titan. Every impact, every gravitational tug sends Hyperion tumbling in a new direction. It's a reminder that not all rotation is orderly. Chaos lurks in celestial mechanics, making some futures fundamentally unpredictable. Enceladus, another of Saturn's moons, has revealed through its rotation that it harbors a global ocean beneath its icy crust. The Cassini spacecraft detected a tiny wobble in Enceladus's rotation that could only be explained by a liquid layer decoupling the ice shell from the rocky core. This subsurface ocean, kept liquid by tidal heating from Saturn's gravity, might be one of the best places in our solar system to search for life. Europa, Jupiter's ice-covered moon, shows similar signs of a subsurface ocean through its rotation. The Hubble Space Telescope has detected water vapor plumes erupting from Europa's surface, possibly giving us access to its ocean without drilling through kilometers of ice. The Europa Clipper mission, launching in 2024, will study these plumes and map the moon's rotation precisely to understand its interior structure. Titan, Saturn's largest moon, rotates synchronously with its orbit, like most large moons. But seasonal changes in its thick atmosphere create winds that actually affect its rotation rate. The Dragonfly mission, scheduled to arrive at Titan in 2034, will study how this moon's rotation interacts with its methane weather cycle and hydrocarbon seas. The study of exoplanet rotation is just beginning. The James Webb Space Telescope can measure wind speeds on hot Jupiters by detecting Doppler shifts in their atmospheres. We've discovered that many hot Jupiters are tidally locked to their stars with permanent day and night sides. Winds exceeding 5,000 kilometers per hour carry heat from day to night, creating complex weather patterns we're only starting to understand. Some exoplanets might rotate in resonances, simple ratios between their rotation and orbital periods. Mercury exhibits a 3:2 resonance, rotating 3 times for every 2 orbits. This resonance, caused by Mercury's elongated shape and elliptical orbit, means that certain locations on Mercury experience double sunrises. The sun rises, reverses direction, sets, then rises again. The search for exomoons, moons orbiting exoplanets, will reveal new examples of rotational dynamics. Large exomoons might be habitable even if their host planet isn't, maintained by tidal heating from rotational energy dissipation. The interplay between an exoplanet's rotation, its moon's orbit, and stellar tides could create stable habitable conditions lasting billions of years. Pulsar planets, worlds orbiting neutron stars, experience some of the most extreme rotational environments imaginable. The first confirmed exoplanets were discovered around Pulsar PSR-B 1257+12, detected through tiny variations in the pulsar's rotation period as planets tugged it gravitationally. These worlds, bathed in intense radiation and magnetic fields, orbit a cosmic lighthouse spinning hundreds of times per second. Looking to the far future, rotation will play a key role in the universe's ultimate fate. As the universe expands and cools, galaxies will exhaust their gas supplies and stop forming new stars. Black holes will dominate, slowly evaporating through Hawking radiation. But even in this cold, empty future, angular momentum will be conserved. The last black holes will still carry the spin inherited from matter that fell into them billions of years earlier. The conservation of angular momentum means that rotation is literally eternal. It can be transferred and transformed but never destroyed. Every spinning atom in your body carries angular momentum that can be traced back through stellar explosions, galactic collisions, and ultimately to quantum fluctuations in the Big Bang. You are, in a very real sense, still spinning with the momentum of the universe's birth. This brings us to one of the most profound mysteries in cosmology. Why does the universe have any rotation at all? In the perfectly smooth, uniform universe predicted by simple Big Bang models, there should be no preferred rotation direction, no angular momentum. Yet everywhere we look, we see spinning objects. The answer lies in those tiny quantum fluctuations in the early universe, amplified by gravity over billions of years into the cosmic ballet we observe today. Recent studies using artificial intelligence to analyze galaxy orientations have found intriguing patterns. Machine learning algorithms examining millions of galaxies from the Sloan Digital Sky Survey have detected subtle statistical preferences in spin directions that might reflect conditions in the early universe. While individual galaxies spin randomly, large-scale patterns might encode information about cosmic inflation, dark matter distribution, or even new physics beyond our current theories. The Vera Rubin Observatory, beginning operations in 2024, will survey the entire visible sky every few nights, tracking how billions of galaxies rotate and evolve. This unprecedented dataset will let us study how rotation connects across cosmic scales, from individual stars to galaxy clusters to the cosmic web itself. We might discover new types of rotating objects, unexpected patterns in cosmic spin, or evidence that challenges our fundamental understanding of gravity and spacetime. Rotation even influences the search for extraterrestrial intelligence. The rotation periods of potentially habitable planets determine their day-night cycles, affecting any possible biosphere. SETI researchers consider rotation when selecting target stars. Planets with extremely long or short days might be less likely to harbor complex life. Radio signals from alien civilizations would be Doppler-shifted by their planet's rotation, creating a characteristic pattern that could help us identify artificial transmissions among natural cosmic noise. The rotation rates of planets might be biomarkers themselves. Earth's 24-hour day is partly maintained by the Moon's gravitational influence. Without our large Moon, Earth's rotation would be chaotic, with the axis tilting wildly over millions of years. This stability has allowed complex life to evolve. When we study exoplanets, unusual rotation patterns might indicate large moons, which could be crucial for habitability. In our own solar system, we're still discovering surprises about rotation. The Juno mission revealed that Jupiter's rotation extends deep into the planet. The famous bands and zones penetrate 3,000 kilometers down. Below that, the planet rotates as a solid body, probably due to the extreme pressure creating metallic hydrogen. This transition from differential to solid body rotation helps generate Jupiter's powerful magnetic field, which extends all the way to Saturn's orbit. Saturn's rotation has been mysteriously difficult to measure because its magnetic field is almost perfectly aligned with its rotation axis, a cosmic coincidence that baffled scientists for decades. The Cassini mission finally determined Saturn's rotation period by detecting waves in the rings caused by vibrations from the planet's interior. Saturn rotates once every 10 hours, 33 minutes, and 38 seconds, a measurement that took humanity centuries to pin down. Uranus and Neptune, the ice giants, have revealed through their rotation that they're fundamentally different from Jupiter and Saturn. Their magnetic fields are tilted at crazy angles and offset from their centers, suggesting their interiors are nothing like the gas giants. The strange rotations and magnetic fields might result from superionic water, a bizarre state of matter where hydrogen atoms flow through a solid lattice of oxygen in their deep interiors. Venus presents the greatest rotational mystery in our solar system. Not only does it rotate backward, it does so incredibly slowly, 243 Earth days for one rotation. Even stranger, Venus's atmosphere rotates 60 times faster than the planet itself, with winds at cloud level reaching 360 kilometers per hour. This super rotation shouldn't exist according to simple models, yet it's been stable for at least decades, probably much longer. Recent radar observations from Earth have detected that Venus's rotation rate varies by up to 20 minutes, probably due to momentum exchange between the dense atmosphere and solid surface. The upcoming Veritas and Envision missions will map Venus in unprecedented detail, perhaps finally explaining why Earth's twin ended up with such bizarre rotation. Mars's rotation is gradually speeding up as it transfers angular momentum to its moon Phobos. This doomed moon orbits so close that tidal forces are pulling it toward Mars about 2 meters per century. In 50 million years, Phobos will either crash into Mars or break apart into a ring system. When that happens, Mars's day will be about 20 seconds shorter, a tiny but measurable monument to the conservation of angular momentum. The Sun's rotation holds clues to its internal structure and future evolution. Different layers of the Sun rotate at different rates, a phenomenon called differential rotation that generates the solar magnetic field responsible for sunspots, flares, and the 11-year solar cycle. The Solar Dynamics Observatory watches the Sun continuously, tracking how rotation patterns change with the solar cycle. Understanding solar rotation helps us predict space weather that can affect satellites, astronauts, and power grids on Earth. As the Sun ages, it's slowly spinning down. The solar wind carries away angular momentum, acting like a brake on the Sun's rotation. Young Sun-like stars spin much faster. Some complete a rotation in less than a day. By measuring the rotation rates of stars at different ages, we can understand how planetary systems evolve. Fast-rotating young stars have powerful magnetic fields and violent flares that might strip atmospheres from close-in planets, while older, slower stars like our Sun provide more stable environments for life. White dwarfs, the endpoint of stellar evolution for Sun-like stars, can spin incredibly fast when they accrete material from companion stars. Some white dwarfs rotate once per minute, approaching their breakup speed. These rapid rotators generate powerful magnetic fields up to 1 billion times stronger than Earth's. The Zwicky Transient Facility has discovered white dwarfs with such strong magnetic fields that they're reshaping our understanding of stellar death and compact object physics. In binary systems where both stars have died, we see some of the universe's most extreme rotation. Double white dwarf systems spiral together, spinning faster as gravitational waves carry away energy. The shortest period system known, ZTF-J 1539 plus 5027, completes an orbit in just 6.9 minutes. The two white dwarfs are so close they could fit within Saturn's diameter, whirling around each other at speeds exceeding 1,000 kilometers per second. When white dwarfs in binary systems eventually merge, they might explode as Type Ia supernovae, the standard candles astronomers use to measure cosmic distances. The rotation of the merging white dwarfs affects how the explosion proceeds, potentially explaining why some Type Ia supernovae are brighter or dimmer than expected. Understanding this connection between rotation and explosion could refine our measurements of dark energy and the universe's expansion rate. Magnetars, neutron stars with magnetic fields a quadrillion times Earth's, might form when rapidly rotating neutron stars undergo a special type of instability. If a newborn neutron star spins fast enough, differential rotation between its core and crust could wind up magnetic field lines like a coiled spring, amplifying the field to magnetar strength. These fields are so strong they would dissolve your body from 1,000 kilometers away by distorting your atoms. The fastest millisecond pulsars spin at the edge of physical possibility. Any faster, and they would fly apart despite their incredible gravity. These cosmic speedsters are recycled, spun up by accreting material from companion stars over millions of years. The accretion process is self-limiting. Spin too fast and the pulsar's radiation pressure prevents more material from falling in, capping the rotation rate at about 750 rotations per second. Some pulsars experience sudden speed-ups called glitches, where they instantly start spinning faster by a tiny amount. These glitches might occur when superfluid vortices in the neutron star's interior suddenly transfer angular momentum to the crust. The Vela pulsar, one of the most studied, glitches about every 3 years. By monitoring these glitches with radio telescopes like Parkes in Australia and Arecibo before its collapse, scientists probe the exotic matter inside neutron stars, matter so dense that a sugar cube of it would weigh as much as Mount Everest. Black hole rotation creates some of the most violent phenomena in the universe. When a star falls into a rotating black hole, it doesn't just disappear, it gets shredded by tidal forces in what astronomers call a tidal disruption event. The star's material forms an accretion disk that can outshine entire galaxies for months. The Zwicky Transient Facility and other surveys detect about one of these events per month, each one revealing details about black hole rotation through the dynamics of the dying star's final orbits. The merger of rotating black holes produces gravitational waves with a characteristic chirp pattern that encodes their spin. LIGO and Virgo have detected black holes spinning at 70%, 80%, even 90% of the maximum possible rate. When these monsters merge, they can receive kicks of thousands of kilometers per second from asymmetric gravitational wave emission, sometimes ejecting the merged black hole from its host galaxy entirely. Imagine a black hole more massive than our Sun flying through intergalactic space at 2,000 kilometers per second, a cosmic cannonball launched by pure spacetime distortion. Recent LIGO observations have revealed black holes with misaligned spins, rotating in different directions relative to their orbit. This suggests they formed separately and found each other later, rather than being born together in a binary star system. The population of black holes we're discovering through gravitational waves is teaching us that stellar evolution and death are more complex than we imagined, with rotation playing a key role in determining a star's ultimate fate. At the largest scales, entire galaxy clusters show rotation patterns that challenge our understanding. The Coma cluster, containing over 1,000 galaxies, appears to have a slight overall rotation. This shouldn't be possible according to standard cosmological models. Clusters should be randomly oriented. If confirmed, cluster rotation would require new physics, perhaps related to dark matter, dark energy, or primordial magnetic fields from the universe's birth. The cosmic web, the largest structure in the universe, consists of filaments of dark matter and galaxies stretching between massive clusters. Recent observations suggest these filaments rotate, spinning around their axes like cosmic drill bits billions of light-years long. The rotation is incredibly slow, taking billions of years per revolution, but the fact that such enormous structures rotate at all is mind-boggling. It suggests angular momentum cascades from the smallest to largest scales in ways we're only beginning to understand. Computer simulations of universe evolution, run on supercomputers like Fugaku in Japan and Summit in the United States, now include rotation at all scales. These simulations show how quantum fluctuations in the infant universe seed rotation that amplifies through gravitational collapse, creating the spinning galaxies, stars, and planets we observe. The Illustris and Eagle simulations have successfully reproduced the distribution of galaxy spins we see in the real universe, validating our understanding of how rotation emerges from cosmic evolution. Dark matter, the invisible substance making up 85% of matter, might rotate in ways we can't directly observe. If dark matter particles interact with each other even weakly, dark matter halos around galaxies could develop rotation patterns that affect visible matter. Some theories suggest dark matter might form dark stars, invisible objects held up by dark matter, annihilation rather than fusion. These hypothetical objects could rotate and might have existed in the early universe, affecting the formation of the first normal stars. The rotation of space itself, frame dragging, has been confirmed by multiple experiments. NASA's Gravity Probe B, launched in 2004, detected Earth's rotation, dragging space-time by measuring tiny changes in gyroscope orientations. The effect is minuscule around Earth but becomes extreme near rotating black holes. Future missions might use frame dragging for navigation or even energy extraction, turning the rotation of massive objects into usable power for spacecraft. Wormholes, if they exist, would likely rotate. A rotating wormhole might be more stable than a non-rotating one, potentially allowing travel between distant parts of the universe or even different universes. The rotation would create closed, time-like curves near the wormhole mouth, raising paradoxes about causality and free will. While wormholes remain theoretical, the mathematics of rotating spacetime suggests possibilities that sound like science fiction, but follow from Einstein's equations. Looking into the deep future, rotation will outlive almost everything else in the universe. Long after stars have died and black holes have evaporated, angular momentum will persist. Subatomic particles will continue their quantum spin. Weakly interacting particles might orbit each other at distances of trillions of kilometers, taking eons to complete single orbits. Even in the heat death of the universe, when entropy is maximized and no more work can be done, the ghost of rotation will remain in quantum fields and curved spacetime. The anthropic principle, the observation that the universe's properties seem fine-tuned for life, extends to rotation. If the fundamental constants were slightly different, atoms might not form stable orbits. If angular momentum weren't conserved, planetary systems couldn't exist. If quantum spin followed different rules, chemistry would be impossible. Our existence depends on rotation at every scale, from quarks to galaxies. This cosmic perspective on rotation changes how we see everyday spinning objects. A child's spinning top demonstrates the same conservation law that shapes galaxies. A figure skater's spin echoes the collapse of stellar nebulae. Water swirling down a drain mirrors the accretion disks around black holes. The same physics operates across 40 orders of magnitude in scale, from subatomic to cosmic. The universality of rotation suggests deep truths about reality. Mathematician Emmy Noether proved that conservation laws arise from symmetries, angular momentum. Conservation specifically comes from rotational symmetry. The fact that physics works the same regardless of which direction you face in space directly implies that angular momentum must be conserved. Rotation is built into the fabric of spacetime itself. Recent discoveries continue to surprise us. The interstellar object Oumuamua, which passed through our solar system in 2017, was tumbling in a complex pattern suggesting it had been rotating for millions of years. Its elongated shape and unusual acceleration sparked debates about whether it might be artificial, though most scientists believe it's a natural object, perhaps a shard of nitrogen ice from an exoplanet. Its rotation carried information about its origin and journey across interstellar space. The second interstellar visitor, Comet Borisov, rotated more conventionally, but showed us that other star systems produce rotating objects similar to our own. As we detect more interstellar objects, possibly dozens per year, once the Vera Rubin Observatory is fully operational, their rotation patterns will tell us about planet formation and destruction throughout the galaxy. Space missions continue to reveal rotational mysteries. The Parker Solar Probe, diving closer to the Sun than any previous spacecraft, has discovered that the solar wind rotates with the Sun much farther out than expected. This co-rotation affects the entire solar system's magnetic environment and might explain anomalies in cosmic ray propagation. Understanding solar wind rotation helps us predict space weather and protect astronauts on future Mars missions. The James Webb Space Telescope is revolutionizing our understanding of rotation in the early universe. It's detecting galaxies that existed just a few 100 million years after the Big Bang, revealing that organized rotation emerged surprisingly early. Some of these ancient galaxies already show spiral structure, suggesting that rotation has been shaping cosmic structure for nearly the entire history of the universe. Future telescopes will push our understanding of cosmic rotation even further. The extremely large telescope under construction in Chile with a 39-meter mirror will directly image exoplanets and measure their rotation periods by tracking cloud features. The proposed LUVOIR telescope concept could detect the rotation of Earth-like exoplanets and even map their continents and oceans by observing how reflected light changes as different surface features rotate into view. The Square Kilometre Array, a radio telescope being built across South Africa and Australia, will detect millions of pulsars, creating a galactic-scale gravitational wave detector. By monitoring how pulsar rotation periods change, we'll detect gravitational waves from supermassive black hole binaries throughout the universe. This pulsar timing array will reveal how the largest black holes in existence spiral together, carrying the angular momentum of entire galaxies. Rotation might hold the key to quantum gravity, the long-sought theory unifying general relativity and quantum mechanics. In loop quantum gravity, space itself is quantized at the Planck scale, 10 to the negative 35 meters. Rotation at this scale might be quantized too, with angular momentum coming in discrete, indivisible chunks. If confirmed, this would mean rotation is pixelated at the smallest scales, like a digital video, that appears smooth but consists of individual frames. String theory, another approach to quantum gravity, predicts that fundamental particles are tiny, vibrating strings. These strings can rotate as well as vibrate, with different rotation modes corresponding to different particles. In this view, the difference between an electron and a quark might simply be different rotational states of the same fundamental string. Rotation would be the universe's way of creating particle diversity from geometric simplicity. The holographic principle suggests that all information in a volume of space can be encoded on its boundary, like a hologram. For rotating black holes, this means their entire interior, including anything that falls in, is encoded on the spinning event horizon. The rotation rate becomes part of the holographic description, suggesting that spin is fundamental to how the universe stores and processes information. Quantum computing might harness rotation in ways we're just beginning to explore. Quantum bits based on electron spin can maintain coherence longer than other types of qubits. Topological quantum computers would use the rotation of quantum states around each other, braiding, to perform calculations immune to certain types of errors. The rotation of quantum states might become the basis for technologies that seem impossible today. In biology, rotation plays surprising roles we're still discovering. Many bacteria have rotating flagella, biological motors that spin at hundreds of revolutions per second. ATP synthase, the molecular machine that produces energy in all living cells, is a rotary engine smaller than a virus. These biological motors are marvels of evolution, achieving near-perfect efficiency by harnessing rotation at the molecular scale. The origin of life itself might have involved rotation. Some theories suggest that life began in rotating droplets or on mineral surfaces with helical defects that concentrated and organized organic molecules. The handedness of biological molecules, why life uses left-handed amino acids and right-handed sugars, might trace back to a slight rotational preference in early chemical evolution, possibly influenced by polarized light or magnetic fields on early Earth. Circadian rhythms synchronized to Earth's rotation are found in almost all living things, from bacteria to humans. These biological clocks are so fundamental that disrupting them increases risks of cancer, diabetes, and mental illness. As we plan for life in space or on other worlds with different rotation periods, we'll need to understand how to adapt or artificially maintain these rotation-linked biological cycles. Climate systems on Earth are dominated by rotation. The trade winds, jet streams, ocean gyres, and weather patterns all stem from our planet's spin. The El Niño and La Niña cycles that affect global weather are essentially changes in how Earth's rotation interacts with ocean currents. As climate change accelerates, Earth's rotation is actually slowing slightly due to melting ice redistributing mass toward the equator, a measurable fingerprint of human activity on planetary spin. The history of understanding rotation is a story of human curiosity overcoming intuition. Ancient Greeks believed celestial objects moved in perfect circles because rotation seemed divine. Galileo's discovery of Jupiter's moons proved other centers of rotation existed. Newton showed that the same force causing apples to fall made planets orbit. Einstein revealed that rotation warps space-time itself. Each breakthrough expanded our cosmic perspective. Cultural perspectives on rotation vary widely. The Sufi whirling dervishes use rotation as meditation, spinning to achieve spiritual transcendence. Tibetan prayer wheels embody the belief that rotation spreads blessings. The Hindu concept of the Wheel of Time, Kalachakra, represents cosmic cycles of creation and destruction. Many indigenous astronomies tracked celestial rotation with remarkable precision, building monuments aligned with rotating heavens. The future of humanity might depend on understanding and harnessing rotation. Space habitats will likely rotate to provide artificial gravity. Fusion reactors might use rotating plasma confined by magnetic fields to finally achieve clean, unlimited energy. Rotating space tethers could launch spacecraft without rockets, using Earth's rotation to fling payloads into orbit. Even interstellar travel might rely on rotating light sails or ramjets that spin for stability. As we search for our place in the cosmos, rotation connects us to everything, The iron in your blood came from supernovae, explosions triggered by collapsing, spinning stellar cores. The gold in your jewelry formed when rotating neutron stars collided. The stable orbit Earth enjoys resulted from countless rotating planetesimals, finding gravitational balance billions of years ago. We exist because of rotation at every scale. Consider this mind-bending fact: because of relativity, observers in different reference frames disagree about rotation. What appears stationary to you might be spinning to someone moving past at high speed, yet angular momentum remains conserved in all reference frames. This means rotation is both relative and absolute, a paradox that highlights the deep mysteries still hidden in spinning spacetime. The quantum Zeno effect shows that observing a quantum system can freeze its rotation. Watch an atom closely enough and it stops evolving, trapped by the act of observation. This suggests consciousness might play a role in rotation at quantum scales, though what this means for the nature of reality remains hotly debated among physicists and philosophers. Recent experiments with ultra-fast lasers can control molecular rotation with exquisite precision, creating molecules that spin in perfect synchronization. This quantum control of rotation might lead to new forms of matter, chemical reactions that proceed in ways impossible in nature, or sensors capable of detecting the tiniest rotational changes, perhaps even gravitational waves or dark matter. The discovery of time crystals, structures that repeat in time rather than space, adds a new dimension to rotation. These exotic states of matter rotate through their configurations eternally, without consuming energy, violating classical thermodynamics while respecting quantum mechanics. Time crystals might exist naturally in neutron stars or the early universe, adding temporal rotation to the cosmic symphony of spinning objects. As we push the boundaries of physics, we're finding rotation in unexpected places. Quantum vortices in Bose-Einstein condensates, ultra-cold atoms that act as single quantum objects, rotate without friction, modeling everything from neutron star interiors to the early universe. These laboratory universes let us study rotation under conditions impossible to achieve any other way. The archaeology of rotation reveals deep history written in stone and ice. Growth rings in billion-year-old fossilized stromatolites show Earth's days were only 18 hours long when these ancient bacteria lived. Coral fossils preserve daily and annual growth patterns, letting us count the number of days per year going back 400 million years. These natural clocks prove Earth's rotation has been slowing steadily, transferring angular momentum to the Moon through tidal friction. Ice cores from Antarctica contain trapped air bubbles that rotated with Earth for hundreds of thousands of years. The orientation of volcanic ash particles in these cores tells us about past changes in Earth's magnetic field, which is generated by rotation in our planet's liquid outer core. These frozen time capsules show that Earth's magnetic poles have reversed hundreds of times, with the field sometimes disappearing entirely during transitions, events that exposed life to increased cosmic radiation. The rotation of tectonic plates shapes Earth's surface in ways we're still discovering. The Pacific plate rotates around a point near New Zealand, grinding against surrounding plates to create the Ring of Fire. GPS satellites can now measure this rotation in real time, detecting movements of millimeters per year. India's northward sprint and rotation as it collides with Asia is pushing up the Himalayas by 5 millimeters annually, Earth's crust literally buckling from rotational forces. Seismic waves from earthquakes change Earth's rotation by redistributing mass. The 2004 Indian Ocean earthquake that caused the devastating tsunami shortened Earth's day by 3 microseconds by pulling mass toward Earth's center. The 2011 Tohoku earthquake in Japan shifted Earth's axis by 17 centimeters. Every earthquake is a tiny adjustment to our planet's spin, recorded in atomic clocks and measured by networks of GPS satellites. The Moon's rotation holds secrets about the solar system's violent past. The lunar far side, hidden from Earth, is dramatically different from the near side: thicker crust, fewer maria, more craters. This asymmetry might result from a collision with a smaller companion moon early in lunar history. The Moon's rotation would have been chaotic after such an impact, eventually settling into the synchronous rotation we see today. Future lunar missions will search for evidence of this ancient catastrophe preserved in far-side rocks. Mars's moons, Phobos and Deimos, have impossible rotations that hint at dramatic origins. Phobos orbits Mars faster than Mars rotates, rising in the west and setting in the east twice per Martian day. This retrograde apparent motion means Phobos must have been captured or formed very close to Mars. Deimos, despite being farther out, is slowly spiraling away from Mars, suggesting a complex orbital evolution, possibly involving a third, now destroyed moon. The asteroid belt contains a graveyard of failed planets whose rotation tells stories of ancient collisions. Vesta, visited by NASA's Dawn spacecraft, has an enormous crater at its south pole that nearly shattered it. The impact accelerated Vesta's rotation and ejected pieces that eventually fell to Earth as meteorites. By studying these meteorites, we can literally hold pieces of a rotating protoplanet that formed 4.5 billion years ago. Rotation in the outer solar system continues to surprise us. Pluto and its largest moon, Charon, are tidally locked to each other, a double synchronous rotation where the same faces always point toward each other. They orbit their common center of mass like a cosmic dumbbell, completing one rotation and orbit every 6.4 days. This mutual tidal locking is rare in our solar system but might be common among binary asteroids and double planets elsewhere. Neptune's moon Nereid has one of the most eccentric orbits in the solar system, suggesting it's a captured Kuiper Belt object. Its rotation period of 11 hours seems ordinary until you realize it's chaotic. The period varies unpredictably due to Neptune's tidal forces. Nereid tumbles through space like a cosmic die, its rotation essentially random over long timescales. This chaos makes Nereid a natural laboratory for studying how rotation becomes unpredictable in multi-body gravitational systems. The rings of Saturn are a masterclass in rotational dynamics. Each ring particle orbits at its own rate, with inner particles overtaking outer ones. Shepherd moons like Prometheus and Pandora confine ring particles through gravitational resonances, creating sharp edges and braided patterns. The spokes in Saturn's B ring, ghostly features that rotate at different rates than the ring particles, might be caused by electromagnetic forces from Saturn's rotating magnetic field levitating tiny dust grains above the ring plane. Jupiter's ring system, much fainter than Saturn's, is maintained entirely by rotation and collisions. Micrometeorites strike Jupiter's small inner moons, blasting dust into space. This dust spirals inward due to electromagnetic forces from Jupiter's rotating magnetosphere, creating rings that must be constantly replenished. Without the source moon's rotation bringing fresh surface material into impact zones, Jupiter's rings would disappear in just thousands of years. Uranus's rings are tilted along with the planet, orbiting over the poles rather than the equator. This unique geometry means the rings appear edge-on, then face-on as Uranus orbits the Sun. The ring's particles experience extreme seasonal variations in sunlight, affecting their orbits through radiation pressure. The Voyager 2 spacecraft discovered that Uranus's rings are kept narrow by shepherd moons, but some rings lack visible shepherds, suggesting invisible moonlets or exotic confinement mechanisms we don't understand. The New Horizons mission to Pluto revealed geological features shaped by rotation over billions of years. Sputnik Planitia, a nitrogen ice plain, sits precisely opposite Charon, stabilizing Pluto's rotation through its mass concentration. This alignment isn't coincidence. The massive ice deposit naturally migrated to this position through true polar wander, where the entire surface reoriented to minimize rotational energy. Pluto literally reorganized itself to rotate more efficiently. Cryovolcanism on rotating moons creates some of the solar system's most spectacular features. Enceladus's geysers, erupting from tiger stripe fractures at the South Pole, are powered by tidal heating from Saturn. But the geysers' locations are controlled by rotation. They form where tidal stresses are maximum. The geysers vary with Enceladus's orbital position, breathing in and out with a rhythm set by rotation and gravity. These plumes might be our best chance to sample an alien ocean without drilling through ice. Europa's chaos terrain, regions where the ice shell has broken and refrozen in jumbled patterns, might result from rotational dynamics. If Europa's ice shell rotates at a different rate than its rocky core, stress builds up until the ice fractures catastrophically. This non-synchronous rotation could explain the global distribution of ridges and bands on Europa's surface. The Europa Clipper mission will test this hypothesis by precisely measuring how Europa's surface features move over time. Io's volcanic activity, the most intense in the solar system, is driven by tidal heating from its rotation and orbit. But Io's rotation affects where volcanoes form. They cluster in patterns related to tidal stress fields. The most powerful volcanoes are offset from where simple tidal models predict, suggesting Io's interior is more complex than we thought. Magma movement within Io might even affect its rotation rate, creating feedback between volcanism and orbital dynamics. Comets change rotation as they approach the Sun, sometimes dramatically. Outgassing jets act like rocket engines, speeding up or slowing down rotation. Comet Hartley 2, visited by NASA's Deep Impact mission, tumbles chaotically due to jets from its peanut-shaped nucleus. Some comets spin so fast they break apart, creating meteor showers when Earth passes through the debris. The rotation of comet nuclei determines where and when jets form, affecting the comet's orbit and whether it survives perihelion passage. The Kuiper Belt and Oort cloud contain billions of rotating objects that preserve the solar system's formation history. These frozen bodies have been rotating in deep space for billions of years, their spins barely changed since formation. When long-period comets fall toward the Sun, they bring rotation patterns from the solar system's edge, telling us about conditions in regions we can't directly explore. Binary asteroids, where two space rocks orbit each other, reveal how rotation evolves through gravitational interaction. The Yorp effect, sunlight pressure on irregular shapes, can spin up asteroids until they fission, creating binary systems. About 15% of near-Earth asteroids are binaries, suggesting rotation-induced breakup is common. The DART mission's impact on Dimorphos in 2022 changed a binary asteroid's orbit, demonstrating how rotation and orbits are coupled in these systems. Contact binaries like Arakoth, visited by New Horizons, formed when two rotating objects gently collided and stuck together. Arakoth's two lobes rotate as one unit now, but preserve evidence of their original separate rotations in their shapes and compositions. These objects are cosmic fossils, preserving the rotation states of planetesimals from the solar system's dawn. As we stand on the threshold of becoming a spacefaring civilization, rotation will determine humanity's future among the stars. Every space habitat we build will need to rotate for artificial gravity, not as a luxury, but as a medical necessity. Without gravity, our bones dissolve, our muscles atrophy, our hearts weaken. The great space stations of the future will be spinning wheels or cylinders, their rotation rates carefully calibrated to provide Earth-like gravity while avoiding the nausea-inducing Coriolis effects that plague smaller rotating structures. The physics of rotating space habitats creates fascinating possibilities and constraints. A Stanford torus, a donut-shaped station 1.8 kilometers in diameter, would need to rotate once per minute to provide Earth gravity at the rim. But anyone climbing toward the hub would experience decreasing gravity, eventually floating weightless at the center. This gradient of artificial gravity could be a feature, not a bug, allowing zero-gravity manufacturing at the hub while people live in Earth-like conditions at the rim. O'Neill cylinders, massive rotating habitats proposed by physicist Gerard O'Neill, could house millions of people in Earth-like environments. These cylinders, perhaps 32 kilometers long and 6.5 kilometers in diameter, would rotate to provide gravity while massive mirrors direct sunlight inside. The engineering challenges are staggering. The structure must be strong enough to contain an atmosphere while rotating, yet light enough to be built with materials we can actually launch or mine from asteroids. But here's the profound truth about cosmic rotation that brings our journey full circle. You are not separate from this universal dance, you are an expression of it. Every atom in your body is executing billions of rotations per second. The electrons in your neurons are spinning, creating the electromagnetic fields that generate your thoughts. The Earth spins beneath your feet, carrying you through space at velocities that would have been incomprehensible to our ancestors. You are a collection of rotations within rotations, a symphony of spins that somehow produces consciousness, wonder, and the ability to contemplate your place in the cosmos. When you look up at the night sky, you're seeing rotation everywhere. That twinkling star, it's rotating, and the twinkling comes from Earth's rotating atmosphere distorting its light. The Milky Way arching overhead, you're seeing our galaxy edge on, looking through the disk we're rotating within. Even the darkness between stars is filled with rotating black holes, spinning neutron stars, and tumbling asteroids, an invisible ballet of angular momentum playing out across the cosmos. The universality of rotation reveals a deep truth about nature. The universe prefers motion to stillness, dynamism to stasis. From the quantum spin of particles to the majestic wheeling of galaxies, rotation is how the universe expresses its fundamental restlessness, its inability to remain static. In a very real sense, the universe rotates because it must, because the alternative, perfect stillness, is forbidden by the laws of physics that emerged in the first moments after the Big Bang. This cosmic perspective transforms how we see everyday rotation. A child's spinning top demonstrates the same conservation laws that keep planets in orbit. Water spiraling down a drain mirrors the accretion disks feeding black holes. The pirouette of a dancer echoes the collapse of nebulae into stars. We are surrounded by echoes of cosmic rotation, fractals of the same patterns repeating across scales too vast for our minds to truly grasp. As we push further into space, we'll discover new forms of rotation we can't yet imagine. Planets with multiple axes of rotation, stars with twisted magnetic fields that defy our models, perhaps even exotic objects where space-time itself rotates in ways that challenge our understanding of physics. Each discovery will add new verses to the cosmic symphony of spin, revealing layers of complexity in what seemed like a simple phenomenon. The search for life beyond Earth will be guided by rotation. We'll look for planets with day-night cycles conducive to life, moons whose tidal heating from rotation might warm subsurface oceans, atmospheric patterns that indicate stable climate systems. The rotation rates of exoplanets might be biosignatures themselves, evidence that large moons or planetary dynamics have created conditions favorable for life's emergence and evolution. Future technologies might harness rotation in ways that seem like magic today. Rotating black holes could be the ultimate power sources, their ergospheres tapped for energy to power interstellar civilizations. Artificial wormholes might need to rotate to remain stable, spinning gateways between distant parts of the universe. Even time travel, if it's possible at all, might require rotating spacetimes that twist cause and effect into closed loops. But perhaps the most profound implication of universal rotation is what it tells us about our cosmic significance. We are not passive observers of a rotating universe, we are active participants in its angular momentum. Every choice you make, every movement of your body redistributes angular momentum in tiny but real ways. You are connected through the conservation of rotation to every star, planet, and galaxy. The universe's spin flows through you, making you a living part of the cosmic dance. As we conclude this journey through the spinning cosmos, remember that rotation is more than just motion. It's memory. Angular momentum preserves the history of every gravitational interaction, every collision, every moment of creation and destruction. The Earth's rotation carries the memory of the moon forming impact. The sun's spin remembers the turbulent nebula from which it formed. Even the electrons in your body carry quantum spin that connects them to the universe's first moments. This is why everything in the universe is spinning, because the universe has a history and rotation is how it remembers. From the quantum to the cosmic, from the beginning of time to its end, the universe expresses its dynamic nature through endless, beautiful, meaningful rotation. We are all part of this cosmic choreography, spinning through space and time on a journey that began with the Big Bang and continues with every turn of every particle in existence. So the next time you see something spinning, a wheel, a planet, a galaxy, remember that you're witnessing a fundamental feature of reality. Rotation isn't just motion, it's the universe's way of being dynamic, of creating complexity from simplicity, of turning the potential energy of position into the kinetic poetry of movement. It's the cosmic engine that drives everything from atoms to galaxies, from the formation of stars to the thoughts in your mind. Thank you for joining me on this exploration of why everything in the universe is spinning. If this journey through cosmic rotation has given you a new perspective on your place in the universe, please share this video with someone who looks up at the stars and wonders. Subscribe to continue exploring the deepest mysteries of our cosmos, and remember, you're not just in the universe, you're part of its eternal dance. Until next time, keep looking up, keep wondering, and never forget that you are made of spinning stardust, forever part of the cosmic ballet that began 13.8 billion years ago and continues with every breath you take. The universe spins, and so do you, beautifully, meaningfully, eternally. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you want to keep exploring the mysteries of the universe, I am sure you will love this other video at the left side of the screen. What's above and below our solar system? Discover what lies above and below the ecliptic, from the sun's polar jets and the mysterious Oort cloud to the galactic halo filled with globular clusters, stellar streams, dark matter, and much more. See you there.